In this video, we are going to first look at elementary matrices, and then we're going to show how elementary row operations can now be done with matrix multiplications of these elementary matrices. And then we're going to define and find determinants of a matrix. So here's a definition for an elementary matrice, which is a lot. What is it? Well, basically, what an elementary matrix is one row operation from an identity matrix. As an example, if you have this I2 and you take row 1 plus row 2 and you put it back into row 1, then this matrix on the right-hand side is an elementary matrix. So we've done one row operation, and it is no longer an identity matrix, but it's only done one row operation. And why do we care? Well, because we can now do row operations on a matrix with a multiplication of an elementary matrix. As an example, here's our matrix A. If we take -2 row 1 plus row 2 back into row 2, this is what we get. If we do the same -2 row 1 plus row 2 back into row 2 on the identity matrix, here's our elementary matrix. Now, if we multiply my elementary matrix multiplied by A, so here's my elementary matrix, here's my A, I get the exact same thing as if I would have done the row operations up here. And you're thinking, well, that's cool. Why do we care again? Because we're going to use this to define properties of determinants in the next section. So elementary matrices do row operations. Here's the theorem. It says, suppose you have A is an n by n matrix, and B is a matrix of the same size that is obtained from A by a single row operation. Then there's an elementary matrix of size M that can convert A to B by matrix multiplication on the left. So that's what this is saying. So this theorem here is saying, hey, if I have this elementary matrix, I multiply it by A, and then I'm going to get this matrix B, which is row equivalent to what we started out with. That's all that says. If the row operation swaps I and J, then we say it is Bij. If we have a multiplier, say alpha, as a scalar multiplier, then B is going to be that row I times that alpha, and then that elementary matrix times A. And if the row operation multiplies I by alpha and then adds to J like we did up here, then we would say that B is I sub J of alpha times A. So that's what we did here. So when we did that -2 row 1 plus row 2 back into row 2, my E was an IJ type move. Again, the book is in the proof is in your book for your viewing pleasure. Other important theorems that we get out of this section is that if E is an elementary matrix, then E must be non-singular. And if A is a non-singular matrix, then there exists elementary matrices so that A would be this multiplication of all these elementary matrices to get A. Again, we're going to really look at this in the next section when we look at properties of determinants. So before we get into determinants, let's define what a submatrix is. Now suppose A is an n by n matrix, then the submatrix, and we're going to note it as A and then I, such that J is m-1, n-1 matrices obtained by removing row I and column J. So in this case, we notice that we have removed the second row. That's what that notation is. So I removed the second row here, and that's how come I've got 1 and the 3 and the 2, -2 and the 5. And I also removed the third column. So that's what the notation is. So I remove row 2 and column 3. In this example, I removed row 3 and column 1. So I removed this row. So this one is I removed row 3, column 1, and you can see that's what that matrix is. And then, of course, this first matrix is I removed row 2, column 3, and you can see the matrix that is remaining here. So the first part tells us the row we removed, and the second part tells us the column that we removed to make that submatrix. And you can tell the submatrix is going to be, if this started out with 3 rows and 4 columns, then my submatrix must be 1 row less and 1 column less. Now, we're going to use that information to do determinants of a matrix. Now, suppose that A is a square matrix, then its determinant, the way we note it as det of A, you sometimes see these with these like absolute values, is an element of C defined recursively by this. You're thinking, okay, what is this saying? Well, let's go through an example. So here's our example. Here is A. Here's my matrix. The determinant of A is, well, I'm going to take and pull out, I'm going to look at this number 3 using my definition above, and I'm going to multiply it by the determinant of the smaller matrix. So this 3 and then this smaller matrix. Now then I go in further and I say, okay, well here's my 3 still. What happened to that smaller matrix? Well, then I do this 1 multiplied by this 2. So there's this 1 multiplied by this 2. And then I would do the 6 multiplied by this -1. So this 6 multiplied by this -1. So this is finding a determinant by doing each individual entry and then breaking down it into the submatrix. So you can see that this entry 3 has removed row 1 and column 1, and it gave me this smaller matrix here. Then if I go into the smaller matrix and remove row 1 and column 1, that's how come I get that 2 right there. So I end up with a -27. Going through all the math. Now if we have a 2 by 2 matrix, we have a nice formula. It says the determinant of A is equal to AD minus CB. And if you're thinking, man, that looks familiar, it should. Because remember, if we have A inverse, if you remember this was 1 over, it was AD minus BC, and there is the determinant of A. When we found the inverse, and then of course I'll finish writing this off, here is DA, those switch position, and B and C switch sign. So there is a relationship between the determinant and the inverse, and we're going to talk about that. So to do as an example, we're going to use this formula that says if I want to find this determinant, I'm going to find the determinant by doing 3 times 4 minus the -1 times 5, which gives me 17. Now my next example, I can actually expand on that theorem from up above. It's kind of interesting. What it is that the first one is the A11, that's where that one comes from. And then I have the A22, that's where that one comes from. And then I have the A2, or the A33, that's where that one comes from. And then I have the A12, that's where the 1 comes from. And then I have the A23, and then I have the A31. And that's where all of these are coming from. And then I have the A13, I have the A21, and I have the A32. And I can continue on. I'm going to have to continue on. And I get all of these numbers. And is that one easier? I don't know. I'm not certain. But there's a formula for it. If you look it on the internet, there's like, hey, here's this great formula for a 3 by 3. Okay, you can get there, but just not a fan. So then we're going to look at finding determinants by expanding out a row. So it says, this theorem says that if you take your determinant and you've got a matrix other than, say, size a 2 or a 3, because 2s and 3s aren't too bad, then I can do it by expanding out a row, kind of like what we were doing before, where I knocked out a row and a column. And we call this, sometimes you might hear this called as the cofactor expansion across the minors. So this proof is in your book for your viewing pleasure. So let's see what this means in terms of the expanding out a row. So if we expand out row 1, A11 would be multiplied by this smaller determinant. A12 would be multiplied by the determinant formed by A21, A23, A31, and A33. And then A13 would be multiplied by this smaller determinant here. So it would give us this. There is a slight shortcut for a 3 by 3 matrix. You may like it, you may hate it. Is that what you do is you take column 1 and you repeat it. You augment on column 1. You take column 2 and you augment it next to that. Then when you multiply down a row, you're just going to strictly multiply down the row, and these will get added together. So when you go down the row, these numbers get multiplied and added together, and you multiply down this row, and you add those together. Now when you multiply in the opposite direction, you're going negative, so these will all be subtracted. And so there is the subtracted. So let's take a look at this example. We're going to do it in two different ways. Or actually, we'll just do it by this, we'll do it by the quick way, slightly quick way. Notice that we repeated column 1 and we repeat column 2. Multiplying down. So I have here 0, 0, times 3 times 1, which is the 0. Then I multiply down this row, which is, or that diagonal, which is negative 2 and 3 and 5, which gives me the negative 30. I multiply down this row, which is the negative, or positive 4, negative 1, and 7, which gives me the negative 28. Now I'm going to multiply down this way, and that's where I get the 0 from. I'm going to multiply down this way, which gives me the 63, and I'm going to multiply down this way, which gives me the 2. I'm going to add all of these together. They just happen to be negative. And then I'm going to add all of these together, and then I'm going to subtract those two numbers, and I get 123. Similarly, is expanding out a column. I can expand out a row. I can expand out a column. So let's take a look at this example where we're asked to find the determinant. I'm going to expand out row 4. So that means I'm going to take out row 4. So this is where the 4 comes from. Now this is the important one. This is the negative. It's always negative 1 raised to the 4 plus that first position. So row 4, first position. And then I end up having this smaller determinant that I'll find from this 3 by 3. And then I'm going to have the 1, negative 1 to row 4, second position. And then when I do that, I'm going to have this and these. That's where this comes from. Okay, I'm just going to erase this because otherwise it's going to get really gnarly. So again, we are expanding out row 4. So now I'm in the third position, so that's where the 2 comes from, is this 2. And then of course my matrix that is being built is this 3 by 3. This 3 by 3. And then I'm looking at my last position, that's 6, negative 1 raised to the 4, row 4th position. And you can see this is the smaller matrix right here. And I'm going to go ahead and find my determinant like I do for a 3 by 3, whatever favorite way you like. And I end up with the 4 is negative because it is negative 1 here raised to the 5th, which means it's a negative 4 down here. And then this determinant is 10. So when I got done with this gave me a determinant of 10. And when I get done, I'm going to do the same thing and with all of those 3 by 3 determinants and negative 1 raised to the 4 plus 1, 4 plus 2, and etc. And I end up with 92. Now, is that the best way to do this? Well, no, actually. when you're trying to decide how to find the determinant, what you're going to want to do is to expand out the row or the column that has the most number of zeros. Because if you expand out the row or column with the most number of zeros, then that means there's less work for you, because 0 times any determinant is going to be 0 all day long. So let's take a look at the next example. Okay, so we're going to now look at the exact same matrix. So here's my matrix up here. It's the exact same matrix. And in fact, I'll write it down here so we can have reference to it. -2, 9, 1, and 4. 3, -2, 3, and 1. 0, 0, -2, and 2. 1, 1, -1, and 6. So, expanding out column 3. Notice when we expand out column 3, this one and this one are being multiplied by the 0. So that just take my work and cut it in half. So when you are doing determinants, what you're going to want to do is you're going to want to choose a column or a row that has the most zeros and expand it out that way. And then you'll still have whatever's left over. This -2 is this -2, row 3, column 3. And then of course the last one would be row 4, column 3, that 2, and that 2, and the matrix that is left over. We still get the same answer, but look, our work has been cut in half. And that's it for determinants. We're going to do our next video, which is going to talk about the properties of determinants, which will make finding determinants even faster. So that's it for now.